Can an airplane fly upside down? Yes, it can. Hello aviators, how are you today? My name is Magnar Nordahl. I'm an airline captain and instructor. According to a common belief, lift is created because the upper surface of a wing is more curved than the underside. When two air parcels are split by the wing, the parcel moving over the wing will have to travel a longer distance than the parcel under the wing before they meet behind the wing. This forces the parcel over the wing to move faster than the other, and according to Bernoulli's equation, an increase in velocity results in reduction of static air pressure, which is lift. This is called the equal transit time hypothesis. If this is correct, then how can an airplane fly upside down? This is what we will talk about today. First, we must understand how a wing creates lift. Some say nobody knows because it's too complicated. Some say it's Bernoulli. Some say it's Newton's third law of motion. Some say it's the Navier-Stokes equations. And if you have read Wikipedia lately, you may say it's the Reynolds average Navier-Stokes equations. Wow, good job. An engineer at Boeing once said, "It's easy to explain how a rocket works, but explaining how a wing works takes a rocket scientist." To kill one myth right away, lift is very well understood by the engineers. They use the Navier-Stokes equations to predict how an aircraft produces lift. But only those with a degree in fluid dynamics will understand those equations. What we need is an easy-to-understand explanation that kids and pilots can understand, without getting the facts wrong. The two most common explanations are pressure difference, promoted by Bernoulli supporters, and Newton's third law, promoted by the Newton supporters. But let me be clear, when it comes to lift, it is not Bernoulli or Newton. They complement each other. Bernoulli is about flow speed, surface pressure, and conservation of energy. And please don't use the term Bernoulli lift. It's not so good. And Newton is about force, flow direction, and conservation of momentum. We are looking at the same thing, but from a different point of view. Maybe you do not care about how a wing creates lift, but wouldn't it be nice to be able to give a correct answer when somebody is asking you? To get it right, we must start with the basics. And just to be clear, when I talk about the fluid, I also mean air. In the science of fluid dynamics, air is a fluid. So get out of your trenches, take a deep breath, relax, and
listen very carefully. I shall say this only once.
Lift is a force acting in the opposite direction of the weight of the aircraft. In a steady horizontal flight, the lift force is equal to the weight of the aircraft. Lift is the sum of the lift coefficient multiplied with half the air density, multiplied with the square of the velocity, multiplied with the wing area. Pilots can control two of those variables, the airspeed and the lift coefficient. The airspeed is true airspeed. The lift coefficient is a dimensionless number that depends on the shape of the airfoil, use of flaps, and the angle of attack. I have made a video about the lift formula, showing how it's used to calculate lift for small and large airplanes. You find a link below. In this video, I will discuss lift created by an airfoil of a wing with an infinite span. Most airplanes designed for subsonic speeds have wings with a rounded leading edge, an upper surface that is more curved than the underside, and a sharp trailing edge. Every wing design is a compromise. It must provide plenty of lift at low speed for takeoff and landing, and be efficient at cruise, while producing as little drag as possible. It must have space for fuel, be strong enough to carry the weight of the aircraft, it must be stiff enough to endure torsional forces, and be flexible enough to absorb turbulence. Here are some definitions. We have the leading edge and the trailing edge. The chord is a straight line from the leading edge to the trailing edge. The camber describes the convexity of the wing. The camber line is an imaginary line halfway between the upper and lower surface of the airfoil. Most aircraft have airfoils with a positive camber, but some have symmetrical airfoil. The angle between the chord line and the airstream is called the angle of attack, and it's very important, in fact more than many people are aware of. Why is the angle of attack so important? Because the lift coefficient increases with increasing angle of attack until reaching 15 to 18 degrees, then the curve drops. The angle of attack where the lift coefficient is at the maximum is called the critical angle of attack. When the angle of attack is increased further, the airflow over the wing separates from the surface and becomes turbulent. The lift decreases rapidly. This is stall. Finally, we have the stagnation point. This is the point along the leading edge where the dynamic pressure is zero, meaning the air is stagnant or not moving. Air flowing above the line leading to the stagnation point will flow up and around the leading edge and over the wing. The air flowing below the line will flow under the wing. The location of the stagnation point depends on the angle of attack. When the angle of attack is increasing, the stagnation point moves down and aft under the wing. Many aircraft have a stall warning system consisting of a movable vane on the leading edge. When the stagnation point moves behind the vane, it is pushed up by the air, activating a buzzer in the cockpit, alerting the pilot about an imminent stall. This graph shows the relation between the angle of attack and the lift coefficient for a Cessna 172. Since the wing has a positive camber, the wing produces lift at zero angle of attack. But the lift coefficient is only 0.28, so the aircraft must travel at a very high speed to stay airborne. At 3 degrees angle of attack, the lift coefficient is doubled to 0.57. This corresponds with a speed of 90 knots at 2000 feet at maximum weight. If we put a symmetrical airfoil on the aircraft, it will produce zero lift at zero angle of attack. To produce a lift coefficient of 0.7, the angle of attack must be increased to 6 degrees. I have taken the liberty to give the symmetrical airfoil the same properties as the cambered airfoil. The stall behavior may be different, but I think you get the point here. Many airplanes used for aerobatics have symmetrical airfoil because it makes it easier to fly upside down. This is a bit special. The wings have a symmetrical profile, and it flies upside down like a charm. Now, can an airplane with a positive camber fly upside down? Yes, but do not try this in a Cessna 172, please. But if it had been certified for inverted flight, the wing would produce zero lift at 3 degrees angle of attack. Again, I took the liberty to give the airfoil the same properties as the first airfoil, but I suspect the stall will be more vicious. Anyway, to be able to produce a lift coefficient of 0.57, it will now need to fly with an angle of attack of 9 degrees. On this picture, you see a formation of Pilatus PC-9 trainers. The wings have positive camber, requiring a higher angle of attack when flying inverted. This is very evident on the picture. To improve lift for takeoff and landing, most wings are equipped with flaps, which increases the camber and therefore the lift coefficient. Many fast aircraft also have leading edge flaps or slats. They allow the aircraft to fly with a higher angle of attack. This is an F-16. The wing is designed for supersonic flight and is very flat. Notice how pointed the leading edge is. This wing is not suitable for flight with high angle of attack because the leading edge is too pointy. Therefore, the wing has leading edge flaps, also called maneuvering flaps. It deflects automatically to increase the camber when the angle of attack increases. Thank you, Mace, for letting me using your video. This is a replica of a Morane-Saulnier Type G from 1912. The wing is thin, but it can still produce a lot of lift because the forward part of the wing is curved. In a way, it's resembling the maneuvering flaps of the F-16, or maybe you should say opposite. The F-16 make a copy of this. It is that curvature that makes the wing effective, because it allows the aircraft to fly with a high angle of attack. The density of the atmosphere depends on the temperature and pressure. At sea level at plus 15 degrees Celsius, the density is 1.225 kilograms per cubic meter. Like all gases, air is compressible. A lesser-known property of air is that it is viscous. Viscosity is the measure of a fluid's resistance to flow and describes the internal friction of a moving fluid. Air has low viscosity, but it is important for lift. When you start studying aerodynamics, you are introduced to theoretical models where viscosity is omitted, so-called inviscid fluids. One example is the circulation theory, which leads to the introduction to the Cotta condition, which in turn requires viscous air. The Cotta condition also requires a sharp trailing edge, which is found on every wing. Static pressure is the pressure in a fluid not in motion. At sea level, the atmosphere has a pressure of 1013 hectopascal, or 10 tons per square meter. This is the weight of the air from the ground and all the way up to space. The pressure acts in all directions and it can be measured with a barometer. An altimeter is a barometer with a scale in feet or meter. Very often is static pressure referred to as just pressure. Dynamic pressure is the kinetic energy of a fluid. It is present when a fluid is in motion, for example wind, or when an object like an aircraft is moving through the air. Airspeed indicators work by measuring the dynamic pressure. And this brings us to Bernoulli's equation. Daniel Bernoulli was studying hydrodynamics when he realized that a moving fluid exchanges its specific kinetic energy for pressure. Bernoulli's equation says the total pressure in a fluid, like the atmosphere, is the sum of static pressure and dynamic pressure. The total pressure cannot change, so when there is a change in dynamic pressure, the static pressure will change accordingly. When an airflow is accelerated, the dynamic pressure is increased, and the static pressure is reduced. This is what happens around an airfoil in flight. Under the wing, the air slows down, resulting in a decrease in dynamic pressure and increase in static pressure. Over the wing, the air moves faster, resulting in an increase in dynamic pressure and decrease in static pressure. I started this video talking about the equal transit time hypothesis. It has been taught to millions of children in science classes, civilian pilots, and even military pilots. But there is a problem. Just ask yourself, how can two air parcels separated by the wing know where the other is? They are not married. We can measure the static pressure around the airfoil and use it to calculate the velocity of the airstream. If the equal transit time hypothesis is correct, then the airflow over the wing will be too slow to reduce the static pressure enough to produce sufficient lift. This wind tunnel demonstration shows the air flowing over the wing reaches the trailing edge a long time before the air flowing under the wing. So the equal transit time is busted. So where did this idea come from? Who is to blame for the equal transit time hypothesis? According to History of Science and Mathematics, this idea originated in Germany in the 1920s, so 100 years ago, and it spread to American and British publications. The source might be this illustration, published by Ludwig Prandtl in 1922. And you might think, oh boy, him? Prandtl? Born in 1875, Ludwig Prandtl is regarded to be one of the most influential scientists in aeronautical engineering. For example, in 1919, he showed that the elliptical spanwise lift distribution is the most efficient. Who has not admired the elliptical wings of the Supermarine Spitfire? Prandtl did not make this illustration to explain lift. He made it to show that the air in the boundary layers will stick to the surface. This happens because of the viscosity of the air. It appears that this illustration led to the belief that air parcels flowing around a wing will meet at the trailing edge at the same time. But as the wind tunnel demonstrated, this is not the case. Remove the boundary layer lines, and you will see that Prandtl otherwise got everything right. The angle of attack, the updraft ahead of the wing, the stagnation point, the compression of the flow lines above the wing, the less dense flow lines under the wing, and the downdraft behind the wing. Conclusion: we can use Bernoulli's equation to explain the relation between differences in pressure and velocity in an airstream. Since the equal transit time hypothesis is busted, how can we explain lift then? Well, there is an easy answer and a more complex answer. So let's start with the easy one. If you want to explain lift in 10 seconds, this is all you have to say. A wing produces lift by turning an airflow downwards. This action, in accordance with Newton's third law of motion, creates an opposite force, which is lift. This is easy to understand, but it does not explain why the air is pushed down. That requires an acceleration of the air. So if your friend is not satisfied, it's time to go to the more complex explanation. And here is where I had a few problems, because how can I explain lift correctly and at the same time simplify it enough to be comprehended by people without education in physics? Normally, an aerodynamic force requires acceleration of a fluid. Therefore, the key for lift is not Newton's third law of motion, but the second. Newton's second law says that the change in motion of an object is proportional to the force impressed. When looking at the streamline around the leading edge, you can see the air is following a curved path. What causes an object to move in a curve? Centripetal force. Newton's second law says the force equals mass multiplied with acceleration. Where does this force come from? The answer is pressure difference. When air is flowing in a curved path, there is a high pressure on one side, pushing the air towards an area with lower pressure. We see this in the atmosphere. Around a low pressure area, the air is flowing with high pressure on the convex side and low pressure on the concave side. The most extreme example is a tornado. And this is what happens when the air is flowing around the leading edge. The higher the angle of attack, the longer the curved path and the stronger the acceleration. And with it, the dynamic pressure increases. And in accordance with Bernoulli's equation, the static pressure decreases. Under the wing, we also have a curved path. Again, the higher pressure is on the convex side and the lower pressure on the concave side. The result is high pressure under the wing and low pressure over the wing. And this pressure difference is lift. This image shows the static air pressure distribution around an airfoil. The black and blue areas are low pressure. The red area is high pressure. Notice how low the pressure is around the upper part of the leading edge. This is where most of the lift is created. And this is why it is so important to keep the leading edge clean and smooth. High-performance gliders are very sensitive to dead insects and water on the leading edge. The rest of the wing is also important, but this is mainly to keep the drag as low as possible. And with increasing angle of attack, also to keep the airstream over the wing attached to the surface as long as possible to delay the stall. This illustration is from Aerodynamics by Clancy. It shows the pressure distribution above and below the wing at different angle of attacks. Note that the lift under the wing is near constant, while the lift over the wing increases with increasing angle of attack. This increases the lift coefficient. However, one question remains unanswered. How does the airfoil direct the air downwards? Why doesn't it go in a straight line behind the upper surface of the wing? So let's go to level 3. It is easy to understand that the underside of the wing directs the airstream downwards, But what about the upper side of the wing? Well, the air can go straight. This happens when the wing is stalled, when you drop out of the sky. The answer to why the air follows the upper surface of the wing is viscosity. As I said, viscosity is the stickiness of a fluid, and it acts like glue. Air has very low viscosity, but it's very important, because no viscosity, no lift. Along the surface of the wing, there is a thin layer where the air is gradually accelerated from zero to the velocity of the airstream. This is the boundary layer. Initially, the boundary layer is very thin, but as the air is moving aft, the boundary layer becomes thicker, and this increases the drag. The behavior of the boundary layer depends on the Reynolds number, which is a dimensionless quantity that describes the ratio between inertial and viscous forces of the airstream. At low Reynolds numbers, the flow is laminar. At high Reynolds numbers, the flow is turbulent. Reynolds number increases with the distance from the leading edge towards the trailing edge. Because of this, air will separate from the trailing edge and move forward along the upper surface of the wing as the angle of attack is increased. And when the wing stalls, most of the air of the wing is fully turbulent. Are you still with me? Congratulations, you completed Chapter 1 towards a degree in fluid dynamics. Just joking. But we can now sum up how a wing produces lift. The most important factors for lift are the shape of the airfoil, the angle of attack, and the airspeed. When the angle of attack is increased, the stagnation points move down and back along the leading edge. This forces more and more air to flow around the leading edge, where it is accelerated, causing the air pressure to drop. This increases the lift coefficient. The air flowing under the wing slows down, resulting in an increase of air pressure. The pressure difference between the top and underside of the wing is lift. The downwash, Newton's third law, is a result of this. Newton's second law rules. The equal transit time is dead, and we can fly into the sunset upside down. Thank you for watching, have a wonderful day, and happy landing.